Why these figures are not included in our book?
That's
Do you have any idea?
You've got the old books, okay? You don't have the new books yet. This is just a general diagram. Don't worry. This is just a basic one to show you what it's a typical system. You don't have that in your new books either. It's just a one for the PowerPoint, just to give you a better diagram. Okay, but you've got the old books there as well, so you won't have this anyway. So we're going to look at these individually as we go through the syllabus. Okay. So let's move on. So a typical starting sequence, I think you might have this one in your old books. Okay, I think we kept that in there as long as I remember right. It's definitely in your new books. So we've got a typical starting sequence of a turbojet. So we've got time along the bottom here. Okay, and we've got percentage of the RPM as it goes up till about self-sustaining when it's running on its own. So when you press the start button, okay, we'll start to get rotation of the engine. So after a few seconds, nothing much really happens. Okay, after about 5 seconds or so, we'll maybe have the HP fuel will go on. 10 seconds or so, you're starting to get light up. And roughly about 20-30 seconds, okay, the start cycle will be cancelled out automatically. This is just a basic generic one. It will vary for whichever engine. But in between here, you'll see you get light up, so we actually get the flame starting. And then we'll get to a point where it's self-sustaining. So if it's self-sustaining, what I mean by that is the engine can run itself. It doesn't need to start the motor any time. So in which case, it will start to speed up and they'll settle off roughly about maybe 58, 59% thereabouts. Okay, like we saw yesterday, anything below 54%, the fade out would cancel circuit. So you're looking about sort of 56 to 58% thereabouts. That's when the idle is now, so the engine is now idle. Temperature represented by the red here. Okay, so after a few seconds, there's no temperature until we get a light up. Then the temperature will rise very, very quickly in the space of a few seconds. It will peak and go slightly above and then come back down. Okay, and it should do that. If it stays high, it doesn't come back down, we've got a problem. All right, so this is just showing you roughly just over maybe 70% maximum TGT, or turbine gas temperature, or EGT. Okay, so it's just a very, very basic generic sort of setup. We're going to look at a far more in-depth starting circuit later on. That's just a typical sort of setup. Now, if you're doing a start and you've got rotation, you've got fuel going in, and you get what's called a hung start. Get a hung start. This is a point where the engine is still rotating, but as you put more fuel in, it's now not accelerating. What will happen is you will see your EGT gauge getting very, very hot and no acceleration, so you have to pull it back. Likewise, a hung start, excuse me, apologies there. Hung start can also be a point when it's rotating and you've maybe forgot to open the throttle, something simple as that. Everybody's been there at some point as a ground runner. You go, why is my engine not starting? Oops, forgot to open the throttle. Because when you do an engine start, you're watching lots and lots of gauges, watching lots and lots of lights, and sometimes you actually forget to open the throttle. Bit embarrassing, but it does happen. So you'll see the rotation, no temperature. Okay, what's gone wrong here? Forgot to open the throttle. Something simple. But if you have opened the throttle, you've added fuel to the combustion chamber, and it's getting hotter, but the RPM isn't going up, that's classed as a hung start. And you have to react quite quick because that could potentially turn into a surge or a stall. Okay, so that's what a hung start is called. Fails to accelerate. Okay, start requires 3 main things in the correct order. And the first one is rotation. Without rotation, we don't get any air coming into the engine. Okay, so we need to get rotation first. We need the air. Once we've got air, we can add fuel by selecting the throttle open. Okay. Once we've got fuel, well, then we can add spark. Okay. Without any one of those, we're not going to get combustion. Okay. So it must be in that order. Rotation first, then we add the fuel, then we add ignition. So if you've got an exam question, they'll say, what is the typical start sequence for gas turbine? What is the requirements? They might give you some of these, but not in the right order. They might say fuel first. Well, there's no point putting fuel first unless you've got air. Okay, so make sure it is in that correct order: rotation, fuel, ignition. Okay. We're going to look at ground starting, using equipment on the ground to help start an engine, and we'll look at things like engine cranking with or without fuel. Now, the terminology we use for that is called dry cranking and wet cranking. I'm going to add that into books later on, but just be aware you can crank the engine or turn the engine over without adding fuel, or you can add with fuel, but the main thing between each of those is there is no ignition. Okay, so we can turn the engine over with or without fuel, but without ignition. We call that cranking, either dry cranking or wet cranking. The occasions when you're going to do that is you might be priming the system, you might be checking a starter motor, that you maybe replace a starter. Okay, normally you just go for a start, or you've replaced several components and you want to do maybe a leak check first before you actually start an engine up. Or it could be a brand new engine and you're getting rid of the inhibiting oil at the fuel system to prime it with proper fuel. Okay. Also for vibration, or you just want to make sure it might have a heavy landing, make sure it's okay for that way as well. And even as we look further down the line, compressor washing, where you're cranking the engine over and you're washing the compressor with a hose or special equipment just to clean the engine. So you don't need to start the engine all the time. So you can actually turn the engine over. Now, cranking can be done with a starter motor, and cranking can also be done by hand cranking, by putting a tool in the gearbox and physically turning the engine over using a socket and a wrench, okay, just to get things moving. You can also start an engine by relighting in flight with or without starter assistance. So some aircraft, when the aircraft used to work on the Nimrod, it used to shut down 2 of its 4 engines when it was at altitude. It didn't need all 4 engines working. It would have the inboard engines working and the outboard engines would be switched off. Now, to relight them, yes, you could use the starter motor, or in this case it was an air starter motor, but used air from the good engine to blow into the other engine and use the air starter to start the engine. Or you can use windmilling. Now, windmilling is when you get the fan to spin by inducing an airflow. So you put the aircraft in a dive, a gradual dive, and once you get the speed of the spool up to a certain RPM, you can open the throttle and put the ignition on, and that should start as well. Okay, so with or without starter assistance. So now we're going to look at the types of starters that we've got that you can use to start your engine. We've got hydraulic starters, big, huge beast of a thing. Cartridge starters, I mean by cartridge, just like a shotgun shell. You know, just a big, it's like a bullet, but there's no bullet attached, it's just a cartridge. It goes bang, so the gas from the cartridge goes onto a turbine, which is connected to a reduction gearbox, which we'll look at shortly. Gas turbine starters, so actually using the air from maybe an APU or from another engine. Windmilling, which I've just mentioned, so propellers can use the windmilling action, and even gas turbines can use the windmilling action as well. Air impingement, again, that could be from the ground or from an APU. A low pressure air starter, electric, just like your cars and motorbikes, just a bigger version. And air starting as well, so we use a lot of air for starting. Hydraulic one, well again, the hydraulic one, purely because of hydraulic power, you can actually spin the engine on that. So a separate hydraulic pump, can use externally to add it on as well. They're not as common nowadays. Some aircraft have them, but they tend to be alternate types. They're quite heavy, quite large, and that as well. Okay, let's just see who's that coming in the office there. All right. Again, the hydraulic one, it's got lots of torque. I mean, it says for light, it can make them quite compact and simple, but it needs a supply of hydraulic pressure and flow. And that makes it heavier and difficult to arrange adequately, so it's not as common. Now the nasty one, isopropyl nitrate, or commonly known as IPN. This is very volatile liquid. It tends to be more for military aircraft. You might have heard of an F-16 type aircraft, fighter aircraft. You have a tank, a separate tank we've got here. and there's usually about 2 gallons of the fluid, the isopropyl nitrate, and we'll give it roughly about 3 potential starts. So squirt some of this fluid in. If it doesn't start the first time, you'll get about 3 starts out of it. Now, the main thing you have to know about this fuel, it's classed as a monofuel. It is self-oxygenating. It provides its own oxygen as it burns. So in other words, it doesn't need the external air. You can't see it, you can't smell it. If you get near it and it's on fire, it will not go out with a normal extinguisher. So do not get it on you, because you will just burn away to a burn away thing. Okay, very, very dangerous, but it does what it's meant to do. Okay, IPN combustion chamber requires no air inlet because it's a monofuel and it burns itself. Careless handling will cause fires and it cannot be extinguished. All it can be done is to cover the fire and let it burn itself out. So very, very dangerous self. If it gets on your skin, it'll pass straight through it and into the bloodstream, and that'll give you a very, very sore head, etc. So again, we tend to use it only on military aircraft. Okay, so a very dangerous. If you see a military aircraft landing in an airport, like an F-16, stay away from it. It's got isopropyl nitrate beside it, or IPN. Very good for starting aircraft, but very, very dangerous. Okay, so it's isopropyl nitrate. Nasty stuff. Carriage starter. Now, this one here, I took this photograph when I was out in Malta, an Air Force Museum, because this is the same engine we've got in the hangar, an old Avon engine. Excuse me. And what it is, inside here, you've got a big, huge cartridge, like a big shotgun shell. And you've actually got 3 of them. There's 1, 2, and then there's one at the bottom. There's 3 of them. So when it ignites, you set it off, the gas will go through the chamber into a diffuser, so you can see divergent shape, and it will hit a turbine. What type of shape of turbine is that?
Impulse.
Impulse, yeah. Centrifugal, that's compressor. This is a turbine, yeah. Impulse, so we just want direct hitting of the gas. We're not bothered about being efficient. We just want to see that gas hit that turbine. Now that turbine is connected to a reduction gearbox. Okay, so if I flip this picture back to front, so here's the front of it now. Okay, so if I flip the picture around, so this will be the front of the engine. There's your 1, 2, and around the side we have 3 cartridges. So you see the gas comes in, hits the turbine. Turbine's connected to this main shaft. There's a reduction gearbox, which is then connected to your spool, engine drive pinion. So you get a lot of torque from this gas, which again, you get 3 chances. You've got 3 cartridges, so 3 chances of starting it. Okay, so it's a slow burning charge. All right, and using to the gearbox. And the type of examples we've got here, this is fitted to a Canberra aircraft, again, an older aircraft. Also Hunter aircraft use them as well. So again, there's the 3 cartridges. One's already taken out. So there's your 2nd cartridge and 3rd cartridge. And just for curiosity, there's your IGVs, okay, or support struts. And behind them, you've got your VIGVs. So going back to the previous day. So when they start, as you see here, you'll hear a big bang and a very high sort of noise like that. And the gas goes down, turns the turbine, turns the reduction gearbox, then turns your spool. Now this engine is a single spool engine, so a very heavy, large compressor and a couple of stage turbine on the back. So it's a single spool engine, so it takes a lot of energy to spin this engine. So hence why you have a reduction gearbox on the turbine to get lots of torque to spin the engine. If you don't catch them the first time, they won't let the engine totally stop. They will try and catch it just before it stops spinning to keep the momentum going. And then if you don't get the second one, you've got your 3rd one. And if you don't get your 3rd one, well, you have to go and change all these cartridges. One aircraft I used to work on, the Hunter aircraft, you had to crawl down the intake. Sorry, there's a hatch underneath the intake. You had to crawl upside and then put these cartridges up above your head and then screw them in. Okay, so 3 charge, and you'd have to clean them out. Every time you fired, a lot of carbon will go in there. You get a breech brush and go and clean them out. But again, very, very old system. This is what's called a Canberra type. So that's a cartridge start. You won't see these on commercial aircraft. Gas turbine starter, yeah, typical APU, little auxiliary pit. Basically, it's a little small gas engine. Okay, and we'll speak about APUs shortly. Okay, so it'll have its own little electric starter motor there. It's got a starter for the starter. Basically, same sort of size as your car starter. That will turn the gearbox, will turn your centrifugal compressor, turbine, etc. What was I going to say there? Yeah, and you can take them out yourself. They're not too big. Some are bigger than others. And just going back to what I did for lunch, there's some drains, okay? You can see some drains here, 1, 2, 3, 4 drains. Now those 4 drains that I spoke about for lunch, if you see a leak come from those drains, you check on your diagram which drain's leaking, and that will tell you if that's okay or not okay. Okay. So yeah, basically a small gas turbine engine to start your big gas turbine engine. That will turn the gearbox or directly onto the engine itself with some sort of clutch mechanism. Quite heavy, again, says, well, largely set to military aircraft, but you do have pretty much the same thing as on a civilian aircraft called an APU. Windmilling, well, you can see in this diagram here, we've got that engine, which is in the feather position, okay? The rest of them here are in the fine pitch, okay, so they're all spinning away. So what will happen is you'll turn this one into the fine pitch, so then it will start spinning because of the air impinging on it, okay? And that will start rotating the propeller, which will rotate the engine, and once it gets fast enough, then you can put the fuel in and ignition on as well. Do that in flight. Air impingement starting. Air impingement starting is light and simple, but it requires a specific ground support. In other words, we can plug an external air hose from a ground power unit, basically a mini jet engine that provides air. We can plug it into maybe a connection there, so in this case this one, and again the air will come in and spin a turbine, impulse type turbine. Again, that'll be in a reduction shaft, and then that will attach itself to the engine gearbox. And there's a shaft for the engine gearbox. That will turn the engine gearbox, and the gearbox will turn your HP spool. Okay. Once it's gone fast enough, the whole mechanism will disconnect using some sort of clutch system and bypass it to disengage the actual start. Because once the engine started, we don't want this container to keep on spinning. So it will disengage through a mechanism within the actual starter itself. Our one to go is a low pressure air turbine starter. Again, light and simple and efficient, and tend to be the main choice of commercial big aircraft. Air pressure can be taken again from several sources: external supply from the ground on an external starter with air power, or internal from another APU as well. Most commercial aircraft will have an auxiliary power unit which can use for electrics and stuff like that, but also supply air to turn an air starter on the actual engine. Very common on most commercial aircraft now. And good old electric starter, same as your cars and motorbikes, same principle. Okay, you have your thermal post, positive and negative. You have your armature, and again in here you'll have a reduction gear, like we saw with the gear mechanism, the sun gears, the planet gears, and a clutch that when it engages, it will push that out, okay, to engage the gearbox. And with the reduction gear, we get lots of torque, and you can spin the gearbox and get the engine started. Common small engines, some fairly heavy engines have some of them, but again, some of the modern starters are now being used on aircraft like 787s. But it tends to be more for the smaller aircraft, but it's very, very similar principle to that of your car or motorbike. Okay. The typical air starting system, yeah, we've got an APU, an auxiliary power unit, at the back of the fin somewhere. And again, basically that's just a mini jet engine itself. So we use the air from that one. Excuse me. Oops, I'm choking up there. Air from that one will be directed by a valve to a control valve in here, which will go to an air valve or air starter, which connect to your gearbox. So that will spin the turbine within the valve, blow the air onto it. That will turn the gearbox, and the gearbox will turn the engine. Okay. Nice and simple. Again, you can use a ground supply. So again, it could be a connection to another engine, and you can have a connection with an exhaust as well as there, or you can have a connection from the ground supply if required. If you've got an APU, you don't always have to start using the APU. The ducting, of these type of pipes. Now these pipes are, you want to make a note of this, is a large bore and they're aluminium alloy, so light and very strong as well at the same point. So these pipes that route all the air, depending on what the source is, you can see some here, there's some of the pipe work there. Okay, there's an isolation valve, so you can select whichever engine and that sort of thing. But aluminium alloy bore, very large, for large volume of air, not very fast, you're only looking about maybe 28, 30 psi, but same sort of pressure in your car tyres, but continuous flow from an APU or whatever. Okay, so large bore made of aluminium alloy. In the valves, the air start valves we use are basically simple on-off valves. So you have a solenoid which will energize, which air will always be available from the APU if you select it, but until you energize it, it won't allow it to move to open the valve. Okay, so once it's opened, the gate will open, the air can then flow through the outside of the valve into the starter itself. Okay, so the air valve. Dead simple. But again, only about 28, maybe 30 psi coming out of there. Then a low pressure air turbine starter, pretty much the same we saw before, better diagram to be honest. You have an air inlet here. Okay, so an LP air supply to the starter. The guide vanes direct it onto an impulse type turbine, which would be that one there. So you have some guide vanes initially. And as it's spinning, it rotates the drive coupling through a two-stage spur epicyclic reduction gear, which you can just see about there. Okay, there's your spur gears, epicyclic type gearing. So we get the torque off that one, and that engages in turn, drives the HP compressor and starts your engine. Okay. Now, we said in the previous one, it incorporates what's called a centrifugal pre-cutout switch. So when this is turning the engine, once the engine comes faster than the starter, that centrifugal cutout switch will be driven from the reduction gearbox, and the engine reaches self-sustaining. Then the speed switch tells the system, okay, thank you very much, I can now carry on myself. We'll de-energize the solenoid in the start control valve and cut off the supply of air to that starter. And as that happens, we've got a clutch mechanism in there. Now this clutch mechanism is the same as you find on push bikes, and we call that a sprag clutch. Okay, what we've got here is sprag clutch. So sprag clutch, when it's rotating normally, okay, you've got the starter ratchet here. There's a carrier connected. So this outer ring here is connected to your HP spool. This is the part that's spinning to start with from your air starter. So as you see the teeth dig into these little arms. That will start to push, in this case, clockwise position. But once this part gets faster, in other words, the engine gets faster than that, it will disengage. Okay, centrifugal force will also put these poles out of the way, and it won't turn anymore. Okay. Sprag clutch or support bearings where the drive sees that the engine would then drive the starter, and furthermore, the pressure regulating valve control fit may fail, too much air overtop the starter and prevent this from causing excessive damage. And you might have a mechanism that actually shears as well to stop that happening. Once you're under high torque, it's held apart by what's called a Belleville washer. Belleville washer will over center and remain in new position until reset manually, and that can only be done when it goes back to manufacturer. Okay. So there's your starter valve. There's actually a starter connected with your tapping from the valve itself. So airflow coming in and an isolation valve, and then we'll blow it into actually your starter itself, just like the one we looked at. A typical ignition type control. In this case, we've got left engine on this side and right engine. You've got start and a stop button, like self-explanatory there. Okay, ignition on. Continuous ignition. Well, we can have continuous ignition if we think there's a chance of a flame out, maybe if we're flying through some rough weather conditions. If we leave that continuous on, that will stay on for at least a minute. If the engine fails, it will reignite and it will continue to stay on for a minute even after the engine has started, just as a safety precaution. Okay. All right. So ignition's great, but it's also very dangerous. We need to make a spark to ignite the fuel, and so we need high voltage. Again, go back to cars and motorbikes. You have high voltage going to the spark plug to ignite the fuel. So lethal voltages, we're looking at 18,000, 25,000 volts. If you get this wrong, you'll get it wrong once. Simple as that. Okay, so make a note of these ones. Stored energy, potentially lethal. Yeah, in the ignition circuits and the systems we use, there is potentially that high voltage in there. It's not the voltage that kills you, that'll burn you. It's the current that's flowing through your body. The voltage supplies the flow. The more current flows through your body, the more chance it is of stopping your heart. Okay, so be very careful with this system. First of all, you'll isolate your LT lead, but actually it should be this way first. Do your circuit breaker first. Okay, do your circuit breaker, isolate your LT lead, which is your low tension lead. This is the lead that provides the power to your ignition system. Okay. Power, you might have to do the fuse as well, depending on time. Then wait at least 1 minute. We're going to look at two types of spark plug, by the way, for a surface gap igniter or a surface spark igniter. If it's a surface gap, which is your standard ones you use on gas turbine engines, you actually disconnected your lead, wait at least 1 minute. Okay. If it's a different type of igniter, wait at least 3 minutes. If it's an air gap, now air gap igniters are like the spark plugs. Again, going back to cars, motorbikes, they're classed as an air gap igniter. So you wait at least 3 minutes. Okay, so 1 minute for a surface gap and 3 minutes for an air gap. Okay. So we're going to look at the module called what's called the high energy ignition unit, or commonly known as an HEIU. Two spark plugs are called igniters, usually opposing, and will provide about 12 to 13 joules of energy, okay, for a high energy ignition unit. Get roughly 1 spark a second. A version of this one is the joule rated unit, and that provides about 2 to 4 joules of energy. Because it's joule rated, it doesn't need much energy because you've got two things going on there. Each system, which is more common for use, is roughly 4 to 7 sparks a second on a dual rated one. So dual rated, less energy, but you've got more sparks, where an HIU version needs more energy, it's only doing 1 spark a second. But because you've got a dual rated one doing 4 to 7 a second, we need less energy. And it can be continuous. We fit in the spark plugs. They're usually in, if you look at a clock face, usually near the bottom, around about 4 o'clock and 7 o'clock position. There's no point putting igniters up at the top because most of the fuel will be at the bottom to start with. Okay. That should be that one. Anything else on that one? Okay. You're getting about 18 to 28,000 volts from the twin one there. Some fade out, as I said there, about 4 to 7 per second. So continuous ignition, pretty much mentioned that already. Switched on, for instance, you've got a stall warning, poor conditions, maybe slushy winter conditions on takeoff. So there's a chance that that water gets sprayed into the intake and potentially cause a flame out. So you'll have it continuous. And as I said there, after stall warning, the igniters will stay active, stay sparking even though the engine started for 1 minute after stall warning has been cancelled, just in case. Okay, make a note of that. There's a dual rated picture of a dual rated one. Dual rated circuits, strange enough, have 2 circuits, one for each charge size, and each ignition unit or HIU receives a low voltage supply controlled by the starting system electrical circuit, and the energy is stored in the unit until a predetermined value. Once it's been done, it will be discharged across the igniter plug. Now, it can be supplied by DC current, your standard 28 volts DC, or operated by what's called the trembler mechanism or transistorized chopper circuit, just a different version of the same thing. And you can potentially have AC supply, maybe 115 volts potentially. DC is generally preferred because that's availability on startup. Your standard 28 volts supply uses a small amount of voltage, which gets stepped up through the actual system. Now this is what's called a DC chamber HEIU. And what we want to look at here is we've got, remember right, get that on there. Yeah, we've got a choke unit, we've got a safety resistor, we've got discharge resistors I like to look at. Okay, so we'll go back to the choke. The choke unit, what that does, that smooths out any pulsations in the charge before it goes to the spark plug, and it also holds on to it. It's almost like a capacitor, it holds its charge. If you ever watch the Iron Man films, there's his little power coming out his hand, you see it building up and then going big spark. Well, he's got a big choke unit in his arm. Without that, you will get a spark, but a sort of intermittent, quite weak spark. So this choke unit holds on and prolongs the spark until it discharges itself into the spark plug. Safety resistor, that's what's there to do. It will sense if there's, in effect, an open circuit. When there's a normal circuit, you'll have there's your HT lead, the high tension lead, and there's your spark plug connecting, so you've got a circuit. If I disconnect the spark plug, I've now got an open circuit, okay? That will be sensed by the change in resistance. Safety resistor will sense that, and it will not allow the spark to happen, okay? Unless you make the circuit. The discharge resistor does what it says. When you disconnect your LT lead, which will come on to in a minute, it will discharge to earth the power that's been stored in the HIU, usually within 30 seconds. That's why, as safety precaution, when you disconnect the LT lead, you wait at least 1 minute, because it depends on the temperature of the day, which can affect the grounding probability. So just in case, we wait a minute for a surface gap igniter or 3 minutes for an air gap igniter. So that's the three main ones I want to look at there. If you look at the box itself, we've got an LT connection and an HT connection. Your low tension connection is the power from the aircraft side, usually a thinner cable. And then your HT connection is your high tension. That's the cable that goes to your spark plug, your igniter plug. Okay, so that'll be a thicker one, and it's usually braided as well. All right, there we go. Okay, that's that one. Here's a typical HT lead. So this would be the one that connects from your HEIU, which goes to your actual spark plug. So you've got a braided sheath around there. Now that braiding, because you've got high voltage going through there, it protects from electronic interference with any other electronic substances, because this braiding is connected to a connector there, or connected to a box which is grounded. So it earths any potential interference from there, because of magnetic fields. We have a main centre core, insulating outer side, all wrapped up in the braiding. Okay. There we go. Earplugs. Again, the two main types I'm looking at is called surface gap, or surface discharge gap, and an air gap. Inside an igniter, though, you'll have your centre electrode, which is your positive, and your outer shell, which will be a negative, some sort of insulator in between, and a coupling nut to join your HT lead on. Here's the two types. So a surface gap igniter plug, as you can see there, is a centre electrode, and it is pretty much in line with the surface of the tip. Hence we call it a surface gap. Now, there are some air gap igniters that look very similar to this, but they're pretty much used in auxiliary power units or indeed piston engines. Standard air gap one is a prolonged electrode with an earth electrode that comes around like that. Now you might have two on each side, okay, and that's your air gap one. So when you're disconnecting this one, you wait for 1 minute. If you're disconnecting this type, you wait for 3 minutes. So yeah, air gaps, APUs, smaller jet engines, and indeed some type of piston engines as well. Potential difference, you get roughly 12 to 25,000 volts on these ones, so it can change a little bit. But again, high voltage. If you disconnect the HT lead first with a power supply, you might end up doing the funky chicken dance. All right, so you'll do it wrong once. Okay, so that was basic ignition. Any questions on that one? hopefully quite straightforward. There's nothing too much. Just double checking, covered that bit. Yeah. Okay. Right, we're going to move on to fire and detection systems next. Okay, so it's all good having fuel, it's all good having oil and ignition, but what happens if we have a fire? We need to be able to sort it out. Yeah. So aviation authorities prescribe conditions under which fire and overheat detection equipment should be fitted. Fire detection must be fitted in all designated fire zones and of all power plants except those of low-powered piston aircraft with a maximum authorised weight of 12,500 pounds or less. So basically, a small aircraft, you don't really need it. You have handheld fire extinguishers. So the bigger commercial, yes, we have to have automatic type systems as well. So what is a designated fire zone? It's a fire zone is a region where potential fire risk can happen. It may exist following a failure, leakage, or any component, equipment part of the power. So in this diagram here, we've got a basic setup. We've got an engine, we've got a loop, a couple of loops here, some sort of management system, and again through your ARINC connector, warning, audible, and some other ignition lights as well. Okay, and obviously we have a discharge guarded button. We don't want them available just to switch off. The important thing here is a fire detection protection system must be able to distinguish between an actual fire and just an overheat. Okay, there's no point in putting the fire bottles off if it's just a slight overheat. And then if you do have a fire, we have no fire bottles to fight the fire with. So we've got to be able to distinguish between a fire, an actual fire, and an overheat condition. So it's directed by the fire authority, designated fire zone, potential risk, failure, leakage, component, etc. Part of the power plant. Requirements. Construction, installation of fire detectors and design of system is such that, so go through all the terminologies, indication of fire is given immediately. We don't want delays, we need to know there's a fire, and occurs in, continues for the duration of the fire. It says there it's recommended that indication of fire has been extinguished should also be given with the minimum of delay. So if the fire has been put out, that's great, we can cancel the circuit and then we can react accordingly. So far as practical, the failure of any component is more likely to render the system inoperative than actually to cause a function spontaneously. The function of any associated electrical circuit may be checked by the flight crew, so we can actually test the fire system without setting the fire bottles off. Okay, and we'll look at a few of those in a little bit. So again, we've got an example here. We've got engine 1, 2, 3, and 4, APU, okay, and some other good bits of pieces. So the main power plant fire detection should contain an audible warning. We call you get this whoop, 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 that sort of sound. You get the warble there. Or the warning may be isolated because if you've got a fire condition going on, you want to be react to it quickly, but you don't want this audible thing going in your ear, so you can actually cancel that once you've highlighted the fact or identified there is a fire. But if a manual cancelling facility is provided, it should be reset automatically when the warning has ceased and should the main warning system. Okay, so once you've dealt with the fire, reset it. It will come back on if you haven't reset it, if you haven't dealt with it. So you can switch the audible off, but you need some sort of indication as well. There must be an approved quick-acting fire or overheat detectors in each designated fire zone, like for combustion, turbine, tailpipe sections, or indeed the turbine engine installations. Must be sufficient, in other words, in numbers and locations, which ensures prompt detection of a fire in those zones. It should be able to withstand vibration, inertia, so we've got acceleration, deceleration, manoeuvres of the aircraft, and other loads that may subject to operation. So it's got to do its job irrespective of what's happening with the aircraft. Must be a means to warn the crew in the event that sensor or associated wiring within the designated fire zone is severed or cut or broken at one point, unless the system continues to function as a satisfactory detection system after it's been cut or severed. Should be a means to warn the crew in the event of a short circuit as well. So you can give an open circuit or a short circuit. And the sensor or associated wiring, again, whichever zone it's in, unless, it continues to work as a satisfactory circuit. No fire overheat detector may be affected by oil or water or any other fluids or fumes that might be present. So yes, you might have a leakage, which is on fire, so you get some fuel leakage out. Well, that should not affect the system. And there must be a means to allow the crew to check in flight the functioning of each fire or overheat detector electrical circuit. Now, a lot of these times they will test these before you start an engine or even an APU, and some of the systems actually will shut down an APU, which we'll describe shortly. All the wiring and other components for each fire or overheat detector system in a fire system must be, strange enough, fire resistant. And no fire or overheat detector system component for any fire zone may pass through another fire zone unless it is protected against the possibility of false warnings, which results in fires and zones through which it passes. Each zone involved is simultaneously protected by the same detector and extinguishing system. So if you've got a separate system that stays within that zone, if you've got one complete system, then fair enough, it can go do that. Each fire detector system must be constructed so that when it is in configuration for installation, it will not exceed the alarm activation time approved for the detectors using the response time criteria specified in the appropriate technical standing order for that detector. In other words, it's got to do what it's meant to do in a specific time. Unless otherwise specified, for compliance with the requirements of the Joint Air Regulations, must be shown by a full-scale fire test or by one or more of the following methods. Tests of similar power plant configurations, tests of components, service experience of airplanes with similar power plant configurations, and analysis. Okay. So detection systems, same zone. We're going to have zones like we saw before lunch. Okay, so we're going to have detector systems in each of these zones. So most of the aircraft, the engine compartments are divided into your two or more zones. Natural engine, the likelihood of fire is most probable in case zone 1. So it will have its own sort of setting there. Overheat warnings result from the leakage of hot gases, which may not cause a fire, but in a period of time cause structural damage to component or adjacent components. So again, like your thermocouples, we don't want to necessarily put the extinguisher out, but we need to figure out, have we got a fire or have we just got an overheat setup? APUs, well, an APU is just a small jet engine. They're protected by a very similar system. Again, sometimes, however, the warning system may also incorporate a normal shutdown system to stop the APU automatically if there is a fire. And what we have is, I think you can see it just about there. You've got an extinguisher or a handle, and you'll have a test button, or this one here. Now, if you press the test button before you start an APU, the fire system will light up. Okay, you'll get a warning on your alarm system there. That lets you know that the system's working. Now, if you start the APU up and you press the fire test button again, it will automatically shut down the APU. I have done this once by mistake. I was just rushing away, trying to get the job done. Went, oh, forgot to test the fire system. I forgot I had the APU already running. Pressed it and it shut the APU down. So it did work. I can prove that. All right, so it has its own system there for an APU. APUs also require an external audible sound, so you'll probably hear this as a klaxon, external horn to sound in the event of a fire, because the APU are designed to run unattended on the ground for long periods. Okay, so basically it has its own self-containing system separate from the engine side. And detection systems, yeah, like we've got here, we've got guarded numbers for each engine. They will light up, saying there's a fault, so a signal from the detector will illuminate, and you'll get obviously the audible sign as well. Okay, continuous indicates temperature conditions in the engine bay and may be used to operate at the warning temperature. The alarm bell or the audible warning device. Test facilities, again, test the continuity of the system. and that sort of thing. Okay, so press to test facility, just like an APU. All right, so we'll look at types of detector. So types of detector we'll find in the system. Usually supplied by your standard 28 volts DC aircraft supply. And we have unit or point detectors. Now these point detectors literally are situated at points most likely to be affected by fire. So they're in the danger zone. And also suitable for overheat detection. Continuous type, that is an average over a temperature in the zone. So these will be like firewire, which we'll come on to shortly. For max coverage of the zone, you'll see these fires and the fire doors and the cowlings of engines, these little thin wires. Well, these are actually a fire detecting wire. Okay. Types of detector. Importantly here, you have to make sure you've got the right type. They might look the same, like this one here. Looks very similar. Okay, but they could be designed to do different jobs. So the main thing is, if you go and fit a detector, even though it looks the same, make sure the part number, okay, is the same. In this case, two different part numbers, both look the same, but they will work in different ways. Pardon me. So the part number is the only positive way of identifying the item and should be compared with the part number as well. They might come as a set for different operating temperatures. So the only way is to say is to check the part number on it. So for different areas, they'll have different settings. So again, make sure, although it looks the same, you fit the right one. First one we look at is what's called a thermal expansion switch. It pretty much does what it says. When it heats up, it expands. Now, in normal situation, this barrel, which is usually sort of steel covering, when it's in normal cool condition, these two contacts, which are attached to one end here and one end here, will be apart. But as that barrel heats up, it's going to expand, isn't it? So as it expands, it's going to pull these connectors at this end and that end, which will bring the contacts down together. And once they contact, that will give the fire warning. Okay, so a steel barrel here, and then what you've got is a pair of silver rhodium contacts. Okay, so these are silver rhodium contacts. So as soon as they touch, that gives a signal, and you're looking at temperatures roughly about 300 degrees. Okay, so at excessively high temperature, we'll get a warning. It gets about 300 degrees. That's enough to expand the steel switch, steel barrel, which will pull these contacts down and make a switch contact. Again, when the temperature drops, the barrel will contract. So as it contracts, it opens out because they're going further back again. So the contacts will reopen, and so it's a reusable contact. But again, make sure you've got the right one, because if you've got another one set at a different temperature setting from maybe further away, that might not react as quick as it should. So again, always check the part number. Differential expansion switch, similar sort of idea, except you've got two types of metal, okay? Two different types of metal called bimetallic strip. The other one will be a heat insulated bimetallic strip. Now usually you've got Invar and steel. So one of these strips will be steel, one of these strips will be Invar. Okay, that's a 2 meter, so two different types of metal. So what will happen is, now depending on the type, as you heat one, one's going to bend. So when two dissolved metals are bond together, they react, change. Okay, so one of them is going to bend out of the way or bend into it. So depending on the type of detector, it will either bend and make a contact or bend away and not make a contact. But again, they will operate the system depending on the type it is. Okay, so again, reaches a certain temperature, it will react. All right. Fusible link. Well, what are fuses for? Or how do fuses work generally? How does a fuse work? Anybody? What happens if you put too much current through a fuse?
Break.
Yeah, it breaks. Yeah, well in this case, it's the same sort of thing. This is held away from the contact. Okay, you've got a spring-loaded plunger trying to pull this plunger down. Well, this fusible joint here, Once basically it melts, well, the spring takes over, brings it down, and makes a contact. The only downside of this system is, yes, this will melt at a certain temperature, but once it's melted, well, that's it. It can't be reused again. It has to be replaced. Like a fuse, like any normal fuse, if a fuse blows, you change the fuse. Well, in this component, you have to change the fuse itself. So it's got a body containing a pair of electrical contacts. One is fixed to the body, and the other is fixed to the plunger. Okay. So again, when this head melts, there's nowhere to hold it up. So the barrel comes down and makes contact. So there's your fixed contact here. I'm going to have to colour this in next time actually. There's your fixed contact. There's your moving contact. Okay, so the spring will take over, move it up, and that's it done. It's contact. But again, it's a one use only. Other types you might come across, well, you probably won't come across to be honest. Pyrotechnic, as it sounds, explosion. Switch consists of metal capillary tube housing, pyrotechnic cord. So a pyrotechnic cord, you set fire to it, it's going to go, yeah? So if you have a fire in your engine compartment, it will ignite with sufficient heat, it'll flame, touches any part, and it'll just blow itself, okay? If this occurs, pressure is generated with the capillary, and this in turn will operate a switch mechanism, and that will activate the warning system in the compartment. But this type of fire is not used on commercial aircraft. Again, more for military aircraft. So you've probably never come across this. Another one is a melting link switch. Again, consists of a pair of contacts held apart by a mechanism which is released with a fusible compound. Melts at a predetermined temperature, so it's like a melting fuse version. And again, like the pyrotechnic flame switch one, the system is not resettable and therefore once only, and therefore not used commercial aircraft. You certainly don't want the pyrotechnic ones on commercial aircraft. If that goes wrong, you've got an explosion. We don't want explosions on commercial aircraft. Detectors. There are two types of thermal detectors. You've got your standard one, standard thermocouple, and a continuous one. Okay. Now, standard thermocouple, where would you find thermocouples in normal day use? Give me an example of some thermocouples, not to do with aircraft. On anything, from your house to your car to your bike, where would you find a thermocouple? Anybody think of thermocouples? Your fridge has got a thermocouple. Your cooker got a thermocouple. If you've got a toaster, it's got a thermocouple. And your cars, you've got a temperature gauge. That's a thermocouple. Okay, motorbikes have the same sort of thing. So quite a lot of different ideas. And the basic principle is you will have a hot zone or hot junction and what's called a cold junction, which is a reference junction. Now this reference junction will have a millivolt supply to it. We don't need much voltage. If you remember back from module 3, if you heat a metal up, that's going to change the polarity of the junction, okay, which will change the resistance. The least resistance will increase the voltage, volts will go up, and that will go to an amplifier to amplify that voltage, and which will go to your gauge or your system. Okay, that's just a basic standard. So the hot zone here, again, we'll use these in exhaust as well. We have exhaust thermocouples, which use the same principle, not for fire detection, but certainly for the exhaust gas temperature. So another form of thermocouple. But certainly we can have thermocouples in a fire system. It does the same thing. Once it gets to a certain temperature, the voltage will go up, and at a certain voltage, it will be multiplied through an amplifier and give a warning in the system. Continuous one, it works similar sort of way, but instead of having a hot reference junction, it doesn't matter whereabout on the actual thermocouple here, we've got a cutaway version, it gives a continuous reading. So, like normal kettles, however, the measuring junction is not formed by directly joining two wires, more by measuring a junction is not fixed, but when subject to an increasing temperature, it becomes concentrated at wherever the hottest part. The hottest part might be here, or the hottest part might be here. That's the reference junction, the measuring junction, so it's continuous. It doesn't matter where it is on that line. Okay. So anywhere along that line, resistance in the insulating material, and the nature of the insulating material between the two wires relates to the highest temperature. And again, that will change the resistance between the compensating cable, like a reference point. And again, that will change the voltage on your reference junction, the cold path, which is your aircraft side. Again, that'll go off to an amplifier and off to your gauge or to your fire system. Which leads us on to firewire. Okay, so what we'll do, go for another quick break in a moment, and then we'll speak about firewire. Okay. All right, folks, that's quarter past. Come back about the conductors. Now, one of these, like this one, is positive, but this time the second one is also soldered to the tube, so that's your outside tube here. So that acts as the negative as well, and that's called a kiddie sensing element. Same again though, your dielectric, the insulation material, will melt at a certain temperature and allow these two to connect and therefore make a circuit. So it's a single element and a double element. Single is Fenwal and the double is kiddie. Okay. Inconel tube on the outside, dielectric insulation, and then when it's single it's positive, when it's double it's positive and negative. Okay. They're the most common ones you'll come across. Operation, it's quite straightforward. You'll have your single loop type system, and you'll have a push the test button to check continuity and that sort of thing, which is always a requirement. Okay, so configured with several heat elements, contain a pair of contacts, okay, and that sort of thing. Yeah, so quite a straightforward one, and depends how long the system is. All right. Okay. Looking at a two-wire thermal switch, again, pretty much the same ones I've got already. It can stand with either an open, I'm going to change that colour actually, I just realised. This type of two-wire thermal switch can withstand either an open circuit or, in fact, a short circuit, so it will work on both. So it's a double protection effect, so either an open circuit or short circuit, and it will still remain functional. We will go into how it works, but to be honest, as long as you remember that a two-wire thermal switch can work on either open or short circuit and still work properly. Okay, so basically you've got a loop of wire going round, pair of contacts, again which will slide, so the thermal expansion, just like we saw the basic expansion switch already. Okay, and another loop which also has a connection as well. So basically, how does that work? Well, you basically got normal operation. You'll have your standard 20 volts DC coming in, supplied to loop A from both ends. If a fire or overheat occurs, or if the test button's pressed, then current will flow through loop B. So yeah, we'll have flow coming in, going through, and that'll make a circuit. Okay, which is fine. There's a sort of setup. This time, the individual ones are set in sort of parallel instead of series before. The previous one was in series, but this time they're in parallel. So it doesn't matter if one fails, we've still got some other ones that will work as well. So if you've got current in loop A, again, it will reset itself. And if we do lose one for whatever reason, we've still got a chance of sensing them as well. Okay. You can read through the operation of loop A and loop B and back forwards, open circuit, short circuit, but just be aware that, to be honest, as long as you remember that they work in open or short circuit, still remain viable, then that's the main thing you need to remember. I'll give you an example of one. You can read the rest as you go through. So I'll give an example of an operation with an open circuit in loop A. So let's say something's happened in loop A. So here's loop A, okay? We've got the volt supply. Here's loop A, okay, to the test switch, and there's loop B. So let's say we've got an open circuit. We've got a fault in here, okay? Something's maybe broken it. So if we've got a fault in there, loop is power from both ends as normal, provides protection similar to single wire. If an open circuit is present loop, power is still available at each terminal switch. Okay, we've still got power available at each terminal switch. Pressing the test button will reveal a condition because for current to flow and light to illuminate, the entire loop has to be secure. With an open circuit in this loop, the light will not show, okay, because it won't go flow back. So we won't get a test circuit as such. Operation with an open circuit in loop B. So this time we've got an open circuit in loop B. Again, the system will still provide fire protection with an open circuit in this loop. Pressing the test button will reveal the fault. The alarm light will not illuminate. Okay. So again, because we've only got one side working, we need both to work, but we won't get it to work this time either. Okay, so just a few examples there. But the system will still operate, you just might not get indication properly. So it's a bit better than the previous one. Go back to the previous one. That's in series. Okay, so just in series, where this time we've got them in parallel with an expansion of a thermal expansion switch. So that's a 2-wire thermal expansion. As long as you remember to say it will still work in open or short circuit mode. This is an example of the single wire continuous loop type system. So you have a monitoring circuit, a test circuit, test switch, and then the sensing element all through the control. Now we've got one back at the hangar we use on an aircraft. It's an old whirlwind helicopter, and we get the students to actually test the output and the input, and they get to read the electronic diagrams. They get to test it, and so far it's still working. So as it goes out, and it comes back in, yeah, on a test circuit just to make sure it's working. Downside is it can be easily damaged. Okay, and there's a lot of connections that connect all the bits. Although it says continuous loop, you will have connections through bulkheads or whatever, or certain parts of the airframe. So there will be a lot of joins. A lot of the faults are purely that haven't been connected properly. So you can take them apart, clean them, put back on, and it should be working. So it could be the kiddie sensing type one, or it could be the Fenwell one. It just depends on which system has been fitted. But that they still do both a continuous loop type one. Again, all supplied by standard 28 volts DC. And I've said before, when it gets back down to normal temperature, it will reset itself. So you can cancel the system out, and providing that you've sorted out the fire, all will be good. We move on to what's called the resistive type. Now we can have 115 volts AC, and we've also got 28 volts DC as well. And the system will activate a warning light as always, and possibly the bell as well. The resistive type, again, using the sort of loop type system, type wire takes the form of a wire embedded in a temperature sensitive material, again contained in an Inconel tube, and joined together with special coupling units to form a loop, just like we saw before. Inner wire and the tube form an inner and outer electric code, and so forth. So some systems, as say, will use 115 volts AC and 20 volts DC. Other systems just use 28 volts DC because that's readily available. In all the conditions, very small standing current passes through the separating material. The current pass is insufficient to operate a control system. So as temperature increases, the resistance of the filling material decreases. So as temperature increases, resistance falls. In other words, get more flow and coefficient of resistance, and that will allow more current to pass through. So when the temperature is risen sufficiently enough, predetermined level, it will operate your warning circuit. When the temperature drops, the dielectric again, set material will return back to the standard insulating abilities, and then it will switch the circuit off. So it's very, very similar to what we've seen on the previous one. It should be noted that the current path is always through the filling material, the dielectric, which governs the strength of the current. Following control, with this arrangement, the warning system is not compromised, and should a break occur in the loop. Okay, so it's not compromised that way. So again, it's a bit safer. So that's a resistive. Then we've got a capacitant. Same sort of system, but very similar. Again, it's not a type of fire wire. Pretty much built around the same way as the resistive one, and looped in the same way. Because of the different type of control, it acts as a capacitance system, with the capacitance of the element increasing as the temperature increases. So a capacitor, remember, a capacitor, go back to module 3, capacitor holds power, it stores power. So this is what this one does. The capacitor increases with heat. The element is then what we call polarized by applying a half-wave rectified AC, way back to module 3 stuff I know, from the control unit, and stores it. and then as it stores it, it discharges it as a feedback current to what's called a silicon controlled rectifier in the control unit during the non-charging half cycles. Okay, way more in depth you need to know, but that's just how it works. So one is as the resistive one, as temperature increases, resistance decreases, so current flows easier. This one, it stores the energy and then dissipates it through a rectifier. Now the advantage of this type is that in the event of a short circuit, again, grounding the element or the system wiring does not result in a false warning. Okay, so two different ways of doing the same thing: resistive or capacitive. Okay, so as I said, to remember the difference between the two, capacitive stores the energy and then sets it out through a rectifier. Resistance, well, as heat increases, resistance decreases, so it allows it to flow easier. Resistive type is probably the most common one, especially in older aircraft, and you might use a capacitive one on the newer ones. Okay, and so just make sure there's the box itself. All right. The diagram, it shows you the wiring connections. You can see the wires all looping round about. Okay, so various areas. Again, they'll be in their zones and that sort of thing. What we're going to look at is what's called a liquid type, or commonly known as a Borden tube. Now, basically, it's a tube filled with a sort of liquid, an inert liquid, so it won't go on fire, obviously. So basically, if you heat something up, what happens, and especially in liquid, it expands. So as this liquid starts to heat up, it's going to actually move this hook. So this hook's going to expand, yeah? So as that expands, it's going to move this arm onto basically a micro switch. It'll make a contact. And likewise, as it cools, it will come back the way, and then we'll remove the micro switch and go back to the normal state. So some sort of fluid, liquid, a short length of tube undergoes a sudden rise in temperature, the liquid will expand and build up pressure, differential, and move it. Now the reason we've got a restrictor in here is because if you just have the same size of tube, that's going to expand quite quick. Yeah, and that could potentially give a false reading or a false indication. So by having a calibrated restrictor, it will allow this to move, but only obviously the engineers that designed this have designed it will move at a certain temperature. Okay, so prevents sudden changes in pressure from giving false warnings in effect. Okay. So action deflects a Borden tube, which causes a pair of electrical contacts, and which again will illuminate your warning, and you might even get a sound bell or horn as well as that. So very simple, through expansion of the fluid, controlled through a calibrated restrictor, we'll then expand that to make a micro switch. Quite straightforward on that one. Now this one's my favourite one, because I call it, it's classed as what's called a pneumatic type detector. So pneumatic, we're looking at air. It's also known as a system donor. The way I remember this one, I call it a doner kebab. All right, that's the way I remember this one. I call it a doner kebab, just because it sounds like doner. All right, so back in there, somebody else in there. So pneumatic type, well, what is it? It consists of a stainless tube again, say around here, and it'll have an inert gas. In this case, we've got helium gas inside there, hydrogen charged core ender, and obviously any heat is going to expand that gas. Okay, so it is due to the properties of that gas, one end of the tube is permanently sealed to retain the inert gas under pressure, and the responder assembly, as it says, is housed at the other end. So when heat is applied for a predetermined level to the element, the internal pressure will increase because it's expanding, and due to expansion loose from the gas and the core material, increased pressure action upon the responded diaphragm operates the alarm switch. So again, we're using a basic principle of expansion. Okay. So as the gas expands, it pushes on the thing and makes a contact, and that's pretty much it. Nothing too hard. It looks a lot more complicated than what it is, but that's what it's called. So a pneumatic type, inert gas, in this case helium. All right, and there we go. Integrity diaphragm contacts are normally closed, signifying the presence of residual gas pressure in the element and the normally open contacts will close in response to increased gas pressure. In other words, when the gas pressure has been heated up, then they will close. And again, all this action is through 20 volts DC. All right, back to normal. Integrity of the element, you want to check it, and the system circuitry is continuously checked using what is called an automatic fault monitor control module, or an AFMCM. Okay, again, just I wouldn't worry too much that one. Just be aware. Won't go through these ones. Be aware of the different types of detectors. Okay, point detectors, the firewire, the names of them, and that sort of thing. So typical values of the sensor element exposed in the heat range is 250 degrees C over the total length of the element, or 380 degrees C or greater over any 5-foot section, okay, or 550 degrees or greater over any 1-foot section. All right. Maybe worth highlighting those in the book. Just check on my page. Again, it'll be different from your one. Let's see if I've highlighted that for myself. Yeah, that's fine. Okay. Some newer type versions got infrared systems. Well, infrared, well, we're looking at lengths of the wavelengths of light. As we have heat, heat produces light. Yeah. Now, every light, we've got the white light, which is a mixture of all the different colours of the rainbow, and those different colours will produce a different wavelength. So by looking at the light generated by heat, we can use this to calculate the type of heat we've got and that sort of thing. Okay, so early infrared systems suffered from a lack of discrimination, as in what they couldn't differentiate between different wavelengths. So if you opened an engine bay panel, it would set off the fire alarm, so it's not very convenient. So now newer systems have been modified to tighten the wavelengths of the units. Radiation emitted from fire crosses the airspace between the fire and detector, and that goes through a window on the actual detector, and the window will look at analyse the broad spectrum of light. And just for example, the filter only allows radiation in a tight waveband, centred around about 4.3 micrometers. Okay. So we look at the radiation. Obviously, the more intensity, the greater the heat. The greater heat is a good chance of a fire. And again, all these voltages will be processed and sent up to set off the alarm. And there's a functional schematic. Again, you're not meant to remember schematics. But again, 12 volt DC supply to ground, got a regulator, and then you have all the good diodes and all the good parts in there, and your sensor off to your signal. Okay, so that's just a typical, but don't panic about remembering that. UV radiation systems, new generation flame detectors being developed in order to overcome problems accounted by wavelength between sunlight and other infrared sources. New systems are concentrating ultraviolet radiation, and the first ones, as I say, where the first UV radiation fire detected system was developed for Concorde. Hence we still teach stuff with reference to Concorde, and the detector was able to operate in temperatures as high as 250 degrees Celsius. Okay, and it was there to detect a flame out, or a flame that's maybe come out of the chamber, combustion chamber, it shouldn't have done. They have been used in some military aircraft, such as the F-111s, the next generation, to give an automatic bite capability, built-in test equipment to check that it's okay. Majority of UV cells in recent years have been fitted to reheat monitoring systems, and we'll speak about these later on. And certainly ones I've used on the aircraft I worked on the RB199 engine on the Tornado aircraft, we use pyranometers to actually check the temperature of the turbine blades, because the heat coming off of those, we can use them as well. All right. Again, we'll speak about more of those later on. Then move on to digital fire detection systems, or commonly known as DFDS, and that's one of the latest ones. It looks very similar to normal firewire, but it's all digital now. Again, now widely used in most commercial aircraft because its reliability, very accurate in detecting fire and overheat situations. Now remember, fire detection systems should differentiate between a fire and also overheat. It looks pretty much identical to the previous forms, except the terminals are completely sealed to prevent ingress of moisture, where the other ones, yes, there's a chance of moisture and some debris could get in there if possible. Make sure you keep them in a dry environment if you're not using them. If they're for storage, place a dust cap over them. And the good thing about these ones, they have an unlimited shelf life. So you don't have to move them every so many hours or whatever. If they get damaged, fair enough, you can understand. While the fire elements are not repairable, the system themselves are fully repairable down to individual component level. So you can repair them, obviously, but to individual components. But otherwise, if they're not broken, leave them alone. They're pretty much there. And there's a digital box that controls it, doing microprocessors and all the good stuff. Is available as a single channel and also dual channel units. Single channel units have one loop of firewire, and therefore dual units have two loops of firewire. And it's the dual unit digital fire detection system that is most widely used. It continuously monitors the resistance and capacitance of the firewire element, and the resistance of the conducting material within the canal tube will reduce, again, like we saw before, with an increase in temperature, just in the resistive firewire. And likewise, capacitance will store it like we saw. So it's a combination of resistance and capacitance, but now in a digital system. And just for good old Module 3, your control unit applies a square wave, if that brings some bells back for your Module 3 days. In the event of a fire overheat, rising temperature will cause the shape to be returned to waveform and change. Additional techniques are employed to determine the resistance and capacitance and reach a preset point and control, and it produces alarm at the correct time. So it's just a fancier version of your standard resistive and capacitive joined together, but all digital and far more accurate. And I'm just showing some typical temperature ranges of operational temperature, an element length in millimeters, so 1 meter, 2 meters, 3 meters, 4, 5, and operational temperature. Again, just an indication of the ones how they will sense temperature. Elements themselves, all connections of the elements are fireproof end fittings. Again, fittings provide environmental seal to exclude moisture, contamination from oils, fuels, etc. They are factory sealed, so you don't seal them. They require no service maintenance, so they have infinite life provided don't get damaged. Standard ring tag terminations, high strength replaceable bolt and lock nut, so there's more chance of replacing the bolt than anything else. And single and dual configurations will continue to function even if the element is cut, and they're all powered from both ends. So if you cut one end, it doesn't matter, it will work up to that point where it's been cut. So it's quite durable. And some ways of mounting them, you've got some rigid pipes to locate them. Okay, and there's you see the digital lens there. There's actually firewire. I mean, it's not very wide. It's the same as the normal resistive and capacitive wire. So be very, very careful. Don't hang tools from them. So you call these rail-mounted ones. 1 or 2 firewire elements, or MEAs, as I say. Again, so they're on maybe on the side of engines for support and very hazardous areas. Types of fittings you'll come across, again, your normal nut and bolt type connection, make sure you keep them clean. Okay, that's the main thing that causes most of the damage. You have these little cam locks that are 90 degrees, don't screw on. They go around, you bolt them onto an area here, and then the little cam lock, it's just a little prong, 90 degree turn, locks it in position. You'll have a grommet or a rubber insert. Now it's split, and the main thing is to make sure the split is not in line with the actual opening part. Put it 90 degrees away and away from the hinge, because it can squash and potentially come out. So quick release once, quarter turn. Note the split of the grommet should be installed at the outer side of the radius of the bend of the firewire. Okay? So it helps take away the stress on it as well. These grommets, these rubber type grommets, they can be black, they can be red. They do wear out through time, so take a chance and make sure you actually look after these. Okay, inspect them with a good torch. The cam locks can vibrate open, so sometimes the little cam lock key can open and then the hinge opens out. So again, make sure they are secure. Okay, so that's pretty much the firewire. sort of scenario. Okay, so know the different types. There's a bit more in-depth information on them in your books. Again, to be honest, just know the different types and you'll be pretty much safe there. So we've got the fire detection and all that. We've now going to look at the fire extinguishing systems and equipment, the bottles and all the other good parts as well. So extinguishing systems in general use are fixed system, so it's bolted into the airframe. A portable system, especially in big aircraft, you have fire extinguishers in the cockpit, maybe on the galley and that sort of thing, but certainly in small aircraft they tend to be fixed military aircraft, or you can have a combination of both. So a fixed system, again, in this aircraft we've got here, looks like a VC-10. We've got an APU with its own extinguisher system. We've got the engines with their own extinguisher systems here. Now normally if you've got two engines, you'll have two fire bottles. You have a cargo compartment possibly as well, and a firewire system within the engine doors and the cells. Permit installed, okay, provide protection of power plants and APUs as required. And sometimes make protection of landing gear, wheelbase, and also baggage compartments, just in case. So operation, basically got a fire extinguisher, not like the normal ones you find in the corridors and your houses and that sort of thing, but it will have an extinguisher of some variety. What's going to be inside is your diaphragm, your bottle, depending on the type it is, a discharge port, you have a ground log, squib, electrical connector, and a discharge assembly, sort of basic one. Normally stored under pressure as well. You need to use that extinguisher. You can't just open it, it falls out. It needs to be under pressure. So again, when you're handling these extinguishers, take care, don't drop them, they will go off. The fire circuits are controlled by switches of fire control handlers in the flight crew in the cockpit. And some types of aircraft, it might be also automatic in the event of crash landing. We used to have things on the aircraft I used to work on, what called crash strips on the wingtips. So if the wingtip hit the ground, these crash strips would make a signal and that would initiate the fire bottles as well. Typical layout, this is for a twin engine one. You've got number 1 engine this side, number 2 engine, and you can actually use either fire bottle for either engine. So let's say with the the engine number 1. Yes, we could use the fire bottle number 1, but if it still was there, we could also use number 2 because we've got a direction control valve. Okay, so pull the handle, sets off the explosive charge, allows the extinguisher to go to number 1 engine. Okay, but it also switches the valve to that side to stop the extinguishment also going into number 2. We don't want that to happen. We want to fill the extinguisher up. But likewise, if we have to use that one again, that will also push this valve across, won't go into that extinguisher, but it will also go to number 1. So we call it a twin shot, 2-shot system. Okay, so we can use either fire bottle for either engine. And this slide valves here, or check T valve, it stops the extinguishing going back into either fire bottle. Along with that, you'll have relief valves for pressure, pressure switching gauge, I'll say explosive catch on there. So again, please be very careful when handling these. They can go off at extreme temperatures, and just be very careful. Okay, what else have we got there? Right. Basic components, again, will vary in construction and shape and size, but are normally comprised of 2 main components. You have a container to keep the extinguisher in there. The container itself is normally made of steel or copper and has an externally, you can see here, threaded neck to which you attach your discharge head, which has explosive cartridge in it. Other types, we have the longer ones here. There's a dual discharge head here. So the container, opening head, banjo bolts, connections, pressure relief, discharge indicator, and that's usually, we'll speak about this now and we'll speak about it again. If it over pressurizes, a little pin will come out. So it's a little telltale to say that, oh, why is that pin out? If you do your servicings on aircraft and the pin has come out, even though it's full, you must take it out and replace it. Okay, you can't just push the pin back in. You have your diaphragm, a flash hole, spigot union discharge, and also that as well. Direction flow valves I mentioned already. So again, on your twin shot system, again, a double check T, so we can have extinguisher for one engine, but we don't refill the other extinguisher. Okay, so non-return valves. Designed to say for a two-shot system, keeps things all happy. All right. Discharge indicators. On the outside of the skin of an aircraft, this is taken from an APU on, I think, one of my old aircraft. You've got discharge and overpressure. So the red will be overpressure and the yellow will be discharge. And these ones just like a paper discharge that if they happen, they'd just be flowing out of the aircraft into the airstream, and that will let us know on a service sign that something's happened. So it lets us know if the extinguisher was discharged, whether on purpose or it's overpressurized or something. You will have mechanical indicators as well. Normally in the discharge head, like I mentioned already, a little pin will come out. Okay, some of those, some you can put back in, but most of the time it's discharged. You don't know if it's empty or if it's full. So what would happen is you would actually replace the bottom. Okay. Discs are generally coloured generally red, but in certain types indicated you might get green discs. And discharge indicators are mounted in structural panels in the cells, so accessible for yourselves as engineers. Electrical indicators, again, several types used in aircraft consist of indicating fuses, magnetic indicators, warning lights, and so on. Again, all connected to the electrical circuit, provide a positive indication of the appropriate cartridge has been fired. Some aircraft have pressure switches, mounting extinguishers, and so on. Again, it all depends on the type you have. So here we go, there's a port one, starboard, left and right of your switch indication. This is still the basic setup. The pipework are steel holes, steel tubes, stainless steel usually with little tiny holes in there. So as the extinguisher gets thrown out into the tubes, it will go to these pipeworks, like spray it out like a diffuser. Okay, so it atomizes the extinguishment into the engine compartment. Because we don't just want a big blob of extinguishing coming out, we need to atomize it. That will hopefully suffocate the flames that are there. All right. The types of extinguisher you might find inside the extinguisher. Bromide used to be in aircraft in my days. It'd be like a sort of purpley coloured type container. No longer used in civilian aviation. It's very toxic, so no point using it in a flight deck or cabin because it'll just suffocate the pilots. And then you won't have to worry about fire. You just have to worry about the aircraft crashing. Okay. Bromochlorofluoride methane, commonly known as BCF. This one you want to remember, and make a note that it's also known as halon 1211. So BCF, or bromochloromethane, is also known as 1211, halon 1211. Semi-toxic, used for aircraft, power plants, and also some portable units. And another halon type is bromotrifluoromethane, or commonly known as BTM. It is also known as halon 1301, used in power plants and cargo hold suppression systems. So definitely remember these two. Methyl bromide, no longer used, very toxic. BCF, known as 1211. BTM, known as 1301. Halon 1301 and halon 1211. Okay, so good ones to highlight there. Remember those ones. Just a quick cap on those ones. Methyl bromide, it boils at minus 4.6 degrees C, nasty stuff. BCF, it's semi-toxic, it says, used for power plants and so on. It has little or no corrosive effect in contact with fire. BCF evaporates instantly, giving rapid flame extinction, so it's very good. Again, it has a boiling point of minus 4 degrees. BTM, used to extinguishers, I've said there, also widely used in cargo compartments and suppression system. It has a boiling point of minus 58. So halon extinction is extremely, I meant to put up here actually as well. BTM, you want to make a note of this, write it down, is also very corrosive to titanium. So you have to be very careful, whatever fire extinction you have, if you use it on the ground, if you put cord on an engine, it's got titanium, and it's certainly aircraft parts have got titanium. It is very, very corrosive. Okay, so try and not use that one where possible. BCF most common. So there's an example of the extinguishers. Okay, fixed elements. As you can see, not the easiest things to take out and put in. They're not usually that accessible, just to make it awkward for you. Pressure gauges. All right, there's the discharge head, and there's the pipe work going off to the spray nozzles. Now, extinguishers before installation, the following checks and inspections should be carried out. Containers should be checked for leakages, dents, corrosion, scoring. Any damage, don't fit them. Nice and simple. There should also be a weight check. Now, once a year, these will be weight checks, just like normal handheld extinguishers. So they will be weighed. Because they might be leaking, they might not show discharge. If they've got a pressure gauge, that's fine. The pressure might be fine, but again, it could be leaking. It makes sure there's no loss of extinguishing. Pin type indicators should be checked. They're flush with the cap, so you put your hand up there, make sure the pin is extending out, saying it's been discharged. And again, you're just checking for normal damage. If you're fitting the ones with the cartridge units to extinguishers, again, check for corrosion, damage. The date of manufacture should be stamped on it. So again, it will tell you the life. Now, a good one to write down is the cartridge has a 5-year storage life, but only a 2-year installation life. Okay. And before you connect the electrical wires up, you'll do a continuity and resistance check. Should be carried out. Basically, what you do is a no volts check. It might be the B2s that do this. Before you put it, you'll fit the container. You put all the plumbing in or the pipe work, and the last thing you connect is the electrical connector. Now, you should do a no volts check, because the last thing you want to do is, if you've got power there and you connect your electrical connector to the extinguisher, there's a good chance that's going to set it off, and you have to change it again. So make sure there's no volts there at all, and connect it once you've done that, and wire lock accordingly. Okay, all good. Again, another example of the type of extinguisher you might have: pressure gauge, backing ring, cartridge, strainer, and so on, and discharge outlet. Again, some more examples of where they're fitted. Okay, so make sure they're properly positioned, supported, locking pins, secured. Always hand them very carefully. Again, if you drop it, it's a good chance you could set it off, and I have seen them go off. It's not very good. Accidental discharge extension may cause injury. You've got that very cold extension coming out. Well, you get instant freezing of the skin, cause a lot of damage, and obviously you're in the area where it's gone off. You can inhale that. That can cause problems as well. So basically, before you fit an extinguisher, make sure you have no power available, circuit breakers, and no volts check, and everything is in the off position. So there's the extinguishers, and there's a close-up of the fire extinguisher rails. You can see the little holes in the rails, which will spray the extinguisher out. And a good check is to make sure, in an engine bay environment, that they are clean and free from debris. Okay, make sure they're not blocked as well. So make sure to give them a good clean, and no obstructions are there. Use some compressed air, some compressed hose or whatever. To prevent enlargement and deformation of holes, should be cleaned only by methods specified in your maintenance manual. Don't go in there poking bits about, okay, because you might affect the metal structure. You can bend them to a certain degree, so cold form is allowed, again in line with your maintenance manual. At the end of the day, make sure everything's secured, ready to go. Okay, and just before I finish for a break, let's just check there. Let's see where we are.
Yes, that's okay.
Yeah, just double checking that as the same as before. Not far off. Part 2. Okay, what I'll do, before going to the valve side of the thing, we'll go for a quick break now. We'll finish off this last part, and then tomorrow we shall do some revision questions. So we'll go for a quick break now. Come back as usual in about 20 minutes. And then we'll finish this last part off, okay? Because it's not far off at all. That'll be book 2 pretty much done. Yeah. Okay. Okay, let's go for a little break for a moment. And we'll
Okay.
back in 20 minutes. Okay. So that's a push for today.
Oh, my God, sir.
Okay, so the last bit of today. It must be getting night time. It's getting dark here, so it must be dark out there. Okay. We'll finish off a little bit, and then basically what's going to happen tomorrow is we'll recap both books 1 and 2 this week. I'm going to try my best to just do a lot of recap tomorrow and start book 3 Monday and Tuesday-ish, which I'll leave sort of Tuesday-ish, Wednesday, Thursday, Friday for book 4. Well, Friday next week, that'll be just purely revision. We'll finish book 4 definitely by Thursday. Because normally we only get 9 days of modules. We tend to finish all the theory on the Thursday. You normally get the exam on the Friday, but you've got an extra day. So we'll try and finish off on the Thursday, expand to then, and then just lots and lots of recap questions on Friday, on Friday. Okay, right, so we'll finish off this little bit we've got left here. And hopefully by next week you'll get new books with a bit of luck, because they've got all the revision questions in them as well, which is good for your revision. So we'll just move on with these last bits. Getting the thing to work. Okay. So move on with valves. It says there the following points should be observed when installing and maintaining the valves. Should be inspected for cleanliness, signs of damage, and freedom of movement. Yeah, makes sense there. Care should be taken to ensure correct location with respect to the required flow of extinguishants. Attachment to respective mountings should be securely made. Yeah, we don't want things loose and falling off. And where appropriate, new sealing rings should be fitted between valve and pipe connections as appropriate. Get all common sense stuff there. Use your manual. Yeah, just a quick recap. Yeah, yellow disc discharge indicators of soil layer, and displaced indicates the bottle cartridge is fired. Red disc indicates the discharge has overheated or overpressurized. Okay, they can be green. It depends on the system, and it can be a different type of window. That's the usual sort of common ones. Weight and pressure checks. Yeah, fully charged weight of extinguisher should be checked at a period specified. It's normally once a year, sometimes every 6 months. It depends. So many hours. Even though it's never been used, the extinguisher will be taken out and sent away to get weighed and checked over as well. And usually the cartridge units get taken off at the same time. Maintenance schedule will determine how when you do that, and before to verify that no loss extinction has occurred. The weight, including the blanket caps, washers, but excluding the cartridge units, is normally indicated on the container or the operating head for an extinguisher body, and so the weight of the switch cable assembly is also excluded. Now, where you've got discharge indicators or fitted and fixed systems, it does not alter the requirement for periodic weighing. Even though the indicator hasn't gone, you still need to be weighed every so often. Even standard fire extinguishers in buildings, they get weighed usually every year to make sure they're okay, even though it's never been used. So things like the date of the weighing and the weight should be specified, recorded on record cards or log cards as we call them, for each type of extinguisher, and also labels on the equipment. If the weight of extinguisher is below that indicated value, it must be withdrawn for recharging. Okay, pretty much you'll take them out of the aircraft anyway and send it off to get checked. You probably won't weigh them unless you're authorised to do so. So relation between pressures and temperatures normally represented in the graph in your maintenance manuals, and certain types of portable ones check is made easier by means of a disc pressure indicator. If the charge pressure below a specified value, this can be pushed in by normal pressure, thumb pressure. But tend not to do that. Okay. Moving on. Storage. Well, you've got explosives in there, so cartridge units must be stored in a sealed polythene bags in a moisture-free atmosphere and kept away from sources of heat. We don't want things going bang when they shouldn't go bang. A label quoting the life expiry date which is generally 5 years from date of manufacture of last overhaul, should be attached to each bag. Now remember, the life expires 5 years, but in use is every 2 years. Okay, so if a cartridge unit is removed from its bag, the life expiry is now 2 years. It's classed as being in use from the date, provided it's still within the normal 5 years. Now, if it's got a life of 5 years and it's come to the 4th year, then when it gets taken in the bag, it won't have 2 years life. It will only have 1 year's life left. So, for example, if it's been on the shelf for 3 years, comes out of the bag, well, it will only have 2 years left. Yeah, so it has to be within that 5-year period. Okay. Anything else? Yeah, should be shelved in direct sunlight. Again, stored appropriately in a safe manner. So that's extinguishers. Okay. And we're going to look at treatment of what to do if you've used an extinguisher or the aircraft's using an extinguisher and that sort of thing. So treatment of a power plant engine after extinguisher contamination. So the engine's had a fire, the extinguisher's been discharged. So what are we going to do now? Okay. So the action taking discharge fire into an engine or engine compartment will depend upon 3 variables. 1, whether the aircraft was in flight or on the ground. 2, the type of extinguishment that was used. 3, whether the extinguishment actually entered the engine or it remained external. Because normally the extinguishment will go round the engine in an engine compartment to put a flame out. But if you're on the ground, there's a chance you might actually put the fire hose into the front of the engine or even the back of the engine possibly. I've had to do it for once real. One of the last jobs and one of the sections I worked on, aircraft landed, taxi down, put the chocks in, shut the engine down, and we carried a bit of servicing. I just got a smell from the back end of something's on fire. So I went around the back of the engine and sure enough there's a flame in the exhaust tube. Now there shouldn't be a flame there, the engine was shut down. What was happening, there was a little leak of an oil pipe, oil was hitting very hot metal and going on fire. So I had to get an extinguisher and put it out. Now it took a few attempts, it wouldn't go out straight away because if you put an extinguisher, which was a BCF one at that time, straight onto a hot surface, what could happen? Thermal shock. So you just a little bit of time, it went out and it was like one of those magic candles that came back on again. So it took about 3-4 attempts before I managed to put the fire out. Only the fire I've had to do is in a hangar. A fuse box go in the top of the hangar, and we managed to switch the power off and put the fire out. But we had to get all the aircraft out just as a precaution. So you've seen lots of fighter aircraft move from a hangar very, very quickly. So hopefully you never have to use one for real. All right, in flight operation of the aircraft fire extinguisher flight, you don't tend to do anything. If it's been used in flight, well, it's going around the engine bay, not an engine, and it'll get extinguished through to atmosphere. Okay, so it's only essential really you're going to do it. Don't be wrong, once you've had an engine fire, you're going to check the engine. Yeah, so you have to check what's going on with it. But if you've got a fire on the ground, if it's externally extinguisher to be put on it, the nacelle extinguisher, you open the doors, the cowls, and vent it for 30 minutes. The last thing you want to do is go and breathe in all that extinguisher. It's not going to do you any good at all. If that means temperature is very low, it's possible that pools of extinguisher may have to be swabbed out with the cloth. So you soak it all up, but vent it first. Obviously let the engine cool down as well, and just let the engine breathe and get rid of most of it. Dry powder. If you use dry powder on an engine, again, if it's externally, open the doors, remove the powder deposits from the engine using an industrial vacuum you have in your stores. But whatever you do, don't wash it down. It will just turn like a gloopy glue, okay? So dry powder, if it's warm, cooled down, brush it off if possible, and then if you can't get quite in there, get a vacuum and to hoover out the extinguishing out. But do not use water. If you use foam, okay, foam extinguisher might be an external leakage as well. Rinse with water again until all traces of the foam have gone, and then if need be, dry it down using an external air supply. CO2, open the cowls again, ventilate CO2. We don't want to breathe that in because there's no oxygen there. Okay, so you need to get that ventilated. It says there, note that although CO2 extinguishers have only a very small quenching effect, there may be thermal shock. on hot parts and engine which need to be checked for cracking and crazing. You've put in a very, very cold CO2 on there, and again, so you have possible thermal shock. So yeah, be very, very careful of that. But that's external. So we just open the doors, clean, hoover, wash down, depending on the type of extinction. Now, if you've had an internal fire and you have actually had to put the flame out inside the engine, again, maybe from the compressor side, it could be from the turbine side. Dry motor or dry crank the engine. If possible, start the engine, run for 5 minutes. I suggest, though, if you've had an engine fire, probably the last thing you want to do is start the engine up. But it could have been just a cylinder or something like that, and somebody's panicked, put the fire out, whatever it is, or it's been a leak, internal leak, you've sorted the leak out. Then dry motor first, so you're going to start the engine without fuel and without ignition. You're just turning the engine over. That's called a dry motor. If you're happy with that, and everything seems to be okay otherwise, then also by dry motoring, you're inducing air in and blowing the extinction out the back of the turbine and the bypass as well. So once you're happy, it's as clean as possible. You might even do your borescope, have a look inside the engine. And if you're satisfied, in theory, well, yeah, go for an engine run, and run it for at least 5 minutes at idle. Don't throttle up, just start it up, watch all your gauges, make sure everything's okay, and check if the leak's outside and that sort of thing. And then check that again. Sometimes it says here, in some engines, it might be necessary to change the oil, because remember, if you're dry cranking, it might have induced some extinction into the labyrinth seal that might have mixed with the oil and gone through the system. So you might have to change the oil. So we drain it, run it, drain it, and run it. Again, all against in accordance with your maintenance procedures. Dry powder, unfortunately, it's to remove the engine and send it off back to the bay. Then they'll strip it down, clean it, and inspect it as appropriately. You can't really clean it out from there. Foam, if you put foam down there, remove the engine again for disassembly and spin it back to the engine bay, and they'll strip it down and clean it. CO2, well, it's just a gas, so really dry motor the engine again, rotate the engine and starter. That'll disperse any residual CO2 that's in there. Again, if everything's good, possible, start the engine, and again, run at idle 5 minutes. But again, note comments on thermal shock. Just be very careful for that one. General requirements, some of the probable cause of false warnings or fail to operate on test are as follows. Ingress of moisture, okay, incorrect assembly of sealing washers or glands or detectors, so poor maintenance, poor engineering techniques. Premature removal of transit caps or seals when fitting new items. In other words, don't take the protective caps off until you're ready to fit it. Don't take them off, leave them at the side, getting covered in dust. Inadequate tightening of connectors. Yeah, make sure everything you fit is torque loaded, and not too tight, not too slack, has to be torque loaded accordingly. So again, with moisture, failed to fit crushed metal sealing washers if fitted when they're fitting a replacement unit. Cracked or chaffed elements, damage. Faulty installation, yeah, detection elements too close to heat shields or other substances which may contain a temperature high enough to actually operate it. So we're getting false indication because we've put it too close somewhere. Circuiting of electrical wiring and chaffing against structures. You make sure that the fire wire and detectors are away from anything that's vibrating or potential moving. Damage to detection components through careless during maintenance. Again, just poor handling techniques. Make sure you fit them properly in the constant manual. That's all we're saying. Inadequate support. So yeah, you've maybe not put it on one of the clips, maybe missed it. More particularly of continuous element detectors with consequent damage from chaffing or fracture through vibration. They're easily damaged. When you open a big kiln door, it's very easy to sit back or lean back on the door, but you could be leaning back on the firewire thing. And some people have seen it. It's a very bad technique. It's hanging tools off firewire. Don't do it. Don't hang anything off firewire. Clip bushes, again, a material unsuitable for the environment, resulting in damage to continuous element at clipping positions. Or things incorrect routing, racking, printed circuit boards, and fire detection modules, possibly resulting in false warnings. And the classic lack of cleanliness, dirt, swarf, anything that shouldn't be in there, mat and electrical connections, causing a short or indeed an open circuit. Keep things clean, Keep your hands clean, so you're handling stuff like this, make sure you're clean as well. Do it in a clean environment. Oil other fluids penetrating connections either before, tightening through incorrect torque loading, and resulting in failure of the insulation. So continuous element detector systems, separate types which are enclosed with an armoured sheath. Continuous elements should be damaged, could be damaged, by rough handling. Also, every precaution must be taken to maintain the efficiency of the system and check its function at frequent intervals. Yeah. So you have your test, you've got your engines, and you've got your fire, and again, fire warning, audible and visual. And make sure you're checking it regularly. Again, you always check your system prior to an engine run and make sure everything's working. That'll be in your pre-start checks. So very crucial, obviously. The last thing you want to do is have an engine fire and you forgot to fit in a fire bottle. Okay, a bit embarrassing. Installation. Okay, before fitting the element, part number should be checked. Like we saw before, the point detectors look similar, but they will be rated for different areas within the aircraft. So make sure you have the correct part number. Don't just pick one out of stores. No, that looks like the right one. Element inspected for cleanness, as usual. Cleanness, damage, and electrical checks should be carried. Ensure continuity and installation resistance are within limits of your relevant maintenance manual. Element should be clipped every 4 inches from end fittings. So maybe highlight this one, guys, and at approximately 6-inch intervals along its length. Clips which are often the quick release, the 90 degrees camel tie, must be positioned so that no damage can be caused to the element by rubbing or vibration. Excuse me. It's also necessary when bending elements and curves should be kept smooth and not less than the minimum radius quoted by the manufacturer. Clip bushes, again, correct positioned at each clip and care taken to remove stain on the element. Excessive bending could result in work hardening capillary, and the kinks or bends are within specified limits and not straightened. Every element will vary in length, and any excess should be spread throughout the actual run of that loop set. Fittings of each element and any other components in the system are protected by caps during storage. Again, the rubber caps that go on, usually coloured red. Again, the caps should only be removed for testing purposes and immediately before coupling up, because it's so easy for a bit of dirt to get in there and cause some problems. I mentioned already, new seal washer must be fitted whenever connection is broken, and all parts must be perfectly dry and clean. Coupling nuts should be tightened, torque tightened to appropriate values. Again, using 2 spanners to prevent twisting. If you just use 1 spanner, you're probably going to twist the actual tube itself. So do the 2 spanner scissor method, as we call it. Different types of control unit are often identical in appearance, and care must be taken to ensure the correct type is fitted. Electric connections to units may be by terminal posts, plugs and sockets, edge connectors or contact buttons, and again, whichever type is used, care must be taken, as always, keep things clean. Change that one. When installation has been completed, operation of the system should be checked by use of the appropriate test switch. And if the test is satisfactory, all nuts which have been reconnected should then be wire locked, because if you go and connect everything up, wire lock it, and then you find there's a problem, you can do it on the wire locking again. So fit it all, route it all, connect it all up, torque tighten it all, go and test it. Once you're happy, great, then wire lock any components that need to be wire locked, unless you're confident that it's going to work straight away. Okay. So there we go, inspection. There's a routine of the fire detection, watching out for sharp bends like that at the joint, which is not very good. Kinks in the cable, long unsupported, so that could vibrate away, all that sort of thing. Acceptance checks, yeah, should be examined externally for damage and may have occurred in transit. So even though you get a new part from stores, give that a check over. Don't just get it and go and fit it like any component of the aircraft. Again, just check for standard damage. Electrical checks as required. Function test it using the appropriate manner in accordance with the maintenance manual. Where's that gone there? You might have to do connectivity test, a continuity or resistance check with the actual element off. So basically, if you're going to do one, you'll ground the electrodes and the outer sheath, the Inconel, and basically if you do positive to your electrode, especially in the Fenwell one, on the outside, there should be no contact. Okay, there should be no resistance there, or no circuit at least. Okay, so it all depends on the type. Periodic checks as required. Again, any damage as per usual, common sense prevails. Anything that doesn't right, look needs repaired, go and sort it out, raise a job cap. Cleaning, when you've got an engine out, that's a good opportunity to keep the bay that it sits in nice and clean. So we can, apart from doing your checks for structural checks, so you will come in and do normal structural checks of the fuselage, pipe work, connections, and it's an opportunity to keep things clean. And checking things like there's a fire wire up there, you can just see it up here where my laser is. Okay, so more fire wire at the back there. Okay, so there's not a lot of room between the engine and the bay. So again, it is easily damaged. Things can vibrate loose and all that. So again, it's worthwhile making sure there's no contamination around about. So use an appropriate tool, even some cleaning fluid that is allowed to be used on it, and dry it off with some air as well, if you have one. Unit detectors, quite straightforward, normally simple DC circuits. So it's slightly different point detectors. There's a number of unit detectors are connected in parallel, so that the actuation of any detector will complete the circuit through a warning lamp. Okay. Inspection and function test. Type of system is checked by using a test switch to simulate the operation of the detector. And this completes the warning circuit. And if the warning lamps light up, it proves you've got continuity of the associated wiring as well. Periodic inspection. Again, at intervals prescribed by the relative maintenance manual, all parts of the system should be examined for security or damage. Continuity, the cables, installation just checks again between shell and leads of each detector. Could be checked with suitable test equipment, multimeter. And that is just about it for firewire and fire detection. Just double check something here. That was all the faults, installation. Yeah. So what we've got tomorrow morning, we've got abbreviations. So what I'll do, I'll leave that for tonight. We'll go through abbreviations tomorrow morning. And then what we'll do some revision questions on book 2, and we'll revise as much as we can, and then we'll do a revision on book 1 as well. Okay, so I'll try not to start, I'll leave book 3 till probably Monday. We'll just do lots of revision book 1 and book 2 tomorrow. We'll just finish, we'll do abbreviations first thing tomorrow and a recap. So where are we there? 4:05. Yeah, that's close enough for myself. Okay, folks, quite a lot to take in today. All right. Tomorrow we'll do the abbreviations first thing, and then just full recap of book 2, followed by full recap of book 1. Okay, any questions so far?
Noted.
All ready to go to bed, already sleepy now. Yeah.
Yeah.
I am. Okay, guys, yeah, so that's pretty much book 2. So tomorrow's probably most revision. We'll just finish off the abbreviations. I won't do them tonight. You'll be bored enough as it is. We'll do those first thing, and we'll have a bit of fun there. And you'll get me, that's what I'm going to do tomorrow. I think you'll get me to draw a circuit. So you'll tell me what to put on, and I'll try my best to draw it for you. Okay, so a bit of fun there, a bit of revision. So lots of revision tomorrow. Okay, folks, if that is it, if nobody's got any question, thank you very much. We shall see you tomorrow, and hopefully the internet will have worked better tomorrow than it did today. But we'll see how it goes. Okay, till tomorrow. Sleep well.
Okay, good night.
Bye for now.
Okay, sir. Thank you, sir. Use it out.
पुरो तनावमा हो नि
सोधै भन्ने मात्रै हो के तनाव
अब बिहान ड्युटी जानुपर्छ सुत्नु पर्न टोली
अनि दाइ के छ त सुत्लिने हो र बुक लिएर आउनु है दाइ कति मार्किङ गर्नु भएको छ हेरौँ है
के मार्किङ गर्ने यार 4 बजे उठ्नु पर्छ यार यस्तो ताल छ यार बर्बाद छ स्थिति
पुष्प दाइ कहाँ बस्नुहुन्छ
चाङनारायण
चाङ्गु हो के
कहाँ हो त्यो भने
चाङ्गु भने अब कहाँ त्यहाँ एयरपोर्टबाट
नारायण भने
अँ,
माथि नै पुग्नुपर्छ कि तलै हो
अलिकति तल माथि भन्दा अलिकति तल
अनि कति 1 घन्टा लाग्दैन तपाईँलाई
लाग्छ नि यार त्यहाँबाट 4 बजे उठ्नुपर्छ भने 5:30 ड्युटी सुरु अनि
ए अनि
4 बजे
केमा
उठेर
आउनुहुन्छ
यहाँ
साधन छ तपाईँसँग
हँ
साधन छ होइन
साधन नभए त कसरी आउनु सबै कुरो।
त्यही त गाह्रो
गाह्रो छ नि त्यही भएर त तनाव खाने नि ग खाने भन्छन् केटाहरूले के हो
कसले गफ हान्यो भने
भर्खर कसले त्यहाँ ग खाने भन्छ भन्दैछ ल है त बाई बाई
ल ल
गुड नाइट सबले गुड नाइट है
ल